In this lecture, we will discuss the topic nuclear energy. There are different types of nuclear energy: fission, fusion, and some say cold fusion, but we will learn all about that. I know nuclear fusion, nuclear energy is not everyone's friend, but we should understand how it works and how the future of this type of energy might be. Let's start with a short history. In the year 1905, Albert Einstein found the famous equation E equals mc squared. That means that mass and energy are in some way the same. And you see, in this equation, there is the c squared. That means c is speed of light, and the speed of light is really, really high. And so you can imagine that if you multiply the mass with a really high number, you get an awful lot of energy. It's incredible. The first thing that this was used, was the nuclear power explosions, but we'll go to that. Knowing this equation does not induce that you can build something that uses that equation. And so it needs some more sophisticated ideas, and Otto Hahn and Lise Meitner. Otto Hahn was the professor and Lise Meitner was an assistant of him, but Lise Meitner really did a good work. He detected on this table, that is a table that really existed, and you can look at it in Munich at the German Museum, Deutsches Museum. They detected that under some circumstances there is Kernspaltung, there is the splitting of atoms, especially of uranium, and thereby not only two parts exist, thereby free neutrons are produced, and this leads to the chance to have a chain reaction. In 1941, Enrico Fermi started to build the first reactor, a nuclear reactor in Chicago. It was done after a very special project started in the United States. It was the Manhattan Project. They wanted to build a nuclear bomb. The reason was, the Second World War and Hitler in Germany. And the danger was that the Nazi Germany will be the first in this race. And so the United States spent an incredible amount of money to be the first in this race. They had no idea how far the Germans really were. So 1941 in Chicago, the first reactor started, and only 4 years later, the first nuclear bomb exploded in Hiroshima, sadly for the people there. This was the end of the war. So everyone was really scared about that, and so the President of the United States, Mr. Eisenhower, had an idea that he said, okay, we did really something wrong, but we have to find a different way, and we have to find atoms for peace. Atoms for peace means we can use the same incredible power for peaceful use in nuclear power stations. And just the next year, the first nuclear-powered submarine started. Nuclear-powered submarines make sense because if you have a submarine, usually you have really troubles to drive the engine. Down there is no oxygen, and so you can't use a diesel generator. You have to use something else, and you can use batteries, but batteries don't really last very long, and you want to be a long time under the sea surface, and so they started a nuclear-powered submarine, the Nautilus, also very famous because it was the first submarine that crossed the North Pole. And the same year, the first nuclear power plant for some way commercial use for using electricity was started in the United States of Russia. Now let's look into the fission process itself. As already mentioned, we can split some types of nuclear cores In this case, we use uranium-235. Now, what's that? Do we have many uraniums? Yes, just every element has different types. They are different heavy depending on the number of neutrons in the core. And so even some very common elements like carbon has different types. You might have heard about carbon 12 and 13 and so on. So uranium-235, due to some details in the core, is able to have this split, this fission process. But be aware, only 0.5% of the natural uranium is 235. Most of it is 238. That is not useful in the moment. So if we want to do that, we have to extract this 007. That is a difficult thing, but okay, we can do that by enrichment. And now a neutron is coming from some neutron source and is going into this core. This nuclear core is excited, and after some billions of seconds, really fast, this core is splitted into two different elements. And what type of elements we produce is by chance. There is no prediction for that. And if you count the numbers, you see 92 and you see 141. That together is 233. Something is missing here, and these are these free neutrons that are leaving. And so together these two elements plus these free neutrons give the same mass that we had from the origin here. And so that is the process. So now we have these two lighter elements, we have the free neutrons, and we have a lot of energy. Now, the interesting thing is these neutrons can now go to the next uranium core, and if there is another uranium, then this will split again and again and again, and we have a type of chain reactor. So this neutron process is going on, the energy can be used, and there is a first problem. And the first problem is here that the light element that typically are generated are radioactive. This radioactivity is not so nice, but we should know that the radioactive decay of these parts is, in the worst case, somewhere in the range of 30 years. So within a human lifespan, most of this stuff will go away. Most of them are really short-living, like iodide, and so 8 days and something like that. Cesium is one of the long-living. Sometimes you hear in the discussion, oh, it will be tens of thousand years. That is in some way true, because some of these neutrons are not exactly doing what they should do, splitting this core. They might be going in a 238 uranium. That is also here, that is a typical natural uranium. And if they are stacked in there, then that produces plutonium. And plutonium is not the thing we really want to see, because that is radioactive over 10,000 years, and it is also possible to produce relatively simple nuclear bombs. So that is the way things go on in this fission. Now, why is it possible that some elements have additional energy if we do this fission process. It should be mentioned that every atom that we find in our universe has to be generated in some place. And actually, at the Big Bang, hydrogen was produced and helium was produced, and some minor amounts of this, and a little bit, by the way, of lithium. So this was at the Big Bang. So only these three elements, hydrogen, helium, and lithium, existed at that time. It's 40 billion years ago. And then this nuclear stuff, these atoms have gone compressed and are in our sun, for example, and sun is now burning this helium to higher elements. And what this scale shows is the binding energy. So every atom has some binding energy inside, and that means, for example, the binding energy of helium is 7, but if you produce oxygen, you have more energy here, and so you can produce oxygen, for example, with 4 heliums. Theoretically, it's not that simple. And then you can produce more and more elements, and there is a final element at top here with the highest binding energy, and this is iron 56. So that's the way usually elements are generated in the sun and in all stars. And so if you look into your body, you will see you are carbon, and that means parts of your body have been carbon a long time ago, have been helium a long time. So, or a star. And now what happens if we want to have all these elements, especially the elements we want to have here? We see they are usually not produced in a star. How then? How do we produce all this stuff? Actually, we don't know exactly, but during the process of a supernova, you might have heard that after a star dies, a supernova can produce that, and the details are still under research, but we know it works. Otherwise, we wouldn't have these elements here. And so we can now look into that, and we see this uranium is also lower than iron, and so we can make it that the uranium is split, especially this 3,5, and going into some other elements here, and then they have a lower energy, and some energy is going into the reactor, and we can heat water, more or less. So that's physics. It's a little bit tricky, but it's good to have an idea what's going on really. So what are the technical problems if we want to do that? So there are some major problems. The first thing is this 235 uranium, that is the one we want to have, is not available in the way we need. So we have to enrich it. That is done by enrichment process up to 3%. It hasn't to be 100%. It's sufficient to have 3%, but that is a difficult process. Usually it's done by centrifugal. So because it's a little bit lighter than the others, we can do this enrichment process. So we don't want to have more enrichment from 3%, because if you have 70%, if you do that for a long time, you can build a nuclear bomb. That is, for example, the problem in some countries like Iran, where they try to use this enrichment process because the machinery is the same, but you are not allowed to do that by international law. So after having this enrichment of 3%, you have to form fuel rods. That is more or less a metallic process, and you put that in the right size, and you can control that easy. And then you have to build a reactor with so-called control rods to switch it on and off. That is also interesting. possible by some special elements like ore. And now this reactor should not have a failure. That means you have to be very careful if you design a reactor of that type. And the engineers did a good work. And a typical modern reactor might go off, as we have seen in Fukushima, under disaster circumstances after an earthquake. But even in this case, the containment of this reactor was not splashed too worse. That should be mentioned. In other cases, like in Chernobyl, we'll come soon to that, it was a little bit worse. It was much worse than in Fukushima. And during the process, you produce plutonium. This is not so nice because you can use it for nuclear bombs. Or we have learned we can use that also, but that's a very difficult process. The plutonium isn't so difficult to produce, but I can tell you, if you want to build a nuclear bomb from plutonium, you have to be very careful, first generating for plutonium, but also the ignition process is much more complicated than in uranium. And most of the states in the world are not able to have this technology. It's impressive that this was done in 1945 at a time where we didn't have microelectronics and high-speed stuff. So energy conversion is now done like in any power station, thermal power station. You have to cool it, and one problem, you have to cool it even after shutdown. That means if you shut down your reactor by the control rods, it's not immediately dying. It is still a little bit hot, and you have to cool it. Otherwise, it will heat itself till a level of temperature that it gets liquid, and then things can go really awful. That didn't happen really in full scale, but we have to be careful. So, and then we have to dispose the spent fuel for a long time because of this plutonium and some other elements that are inside the fuel rods. Now, look into the power plant. So this is a very, very simple sketch of this power plant. We see we have this simple basic setup. In here, this is the hot area, there is the uranium. And so these are the control rods, and that's all encapsulated in a big iron vessel. And this vessel derives now a water cycle in this way around. Let's follow the arrow. And this water cycle is containing hot water, of course. And this water cycle is then exchanging its energy to another water cycle. And this water is then running through a turbine and going back to this. So this is the second cycle. Now, because that is very hot water, you have to cool it. And so we have even a third cycle, and this is this one in the cooling tower. So we have this exchange points of energy. The first is the exchange at the hot side where the reactor is. Then we have an intermediate side. Then we have a generator. And then we have a side for the cooling, and the cooling tower is the cold place. We always need a hot and a cold place if we do a simple power station. Now, if we look into the price of that, and we should understand that the price is very low. For fuel is 0.5 cent per kilowatt hour. But all the cost comes in if you look into the safety. The safety is the expensive part in this. How expensive it has to be, that's a different question. We talk a little bit later about that. Now, after this turbine, of course, there's a generator, and this generator is bringing your electricity into the grid. So that is the electricity you are interested in. Now, what's the advantage of this type of energy production? You can have a continuous production. Different to solar energy, it works 24 hours a day. So you have a 24 hours, and you even at weekends it works. So 24/7, that means we have always power. Sometimes we have more power than we need. That might be sometimes a problem, but we don't have gaps as in solar and wind power. That is a real advantage. The second thing is that power stations need space, but you have a small land demand due to this high energy density. That is a significant point, because if you have traveled through Germany, you have seen a lot of wind generators, and they need space, and not everyone likes the land side completely full with rotators. And if we want to do that in the Black Forest, we have to put about 8,000 of them in the Black Forest. Let's see what will happen. One of the biggest advantages is that we don't have chemical air pollution. This is a very significant point, because we will learn that air pollution is not healthy. It can generate dust and NOx and so on, and that might bring death to some people and not so few. There is also something that is not going out here, is carbon dioxide. Carbon is this element and this gas that might heat and will heat our Earth, and we have to be careful. We have only one Earth, and we have to be careful about that. So the resource, uranium and thorium, I didn't talk about thorium, that will come a little bit later, is an abundant element. We can use it for maybe at least 1,000 years, but we will see. The waste is here, but the volume of the waste is quite small, and if we count, the death toll per terawatt hour is very low. Now we will see that in more detail. If we count that, we see that, for example, coal, and that is the average number. This was done by different institutes, and that's a publication from Forbes. If you have 1 trillion kilowatt hours, that's a lot, that's a kilowatt hour, you have 100,000 people dying from the air pollution. That's a very high number. Now, it should be mentioned, it depends on the quality of the power station. If you have a high standard power station in the United States, you have only 10,000 per trillion kilowatt hours. And yeah, trillion kilowatt hours. What's this? That's in our list. You can check it. It's a petawatt hour. It's 1,000 terawatt hours. It is 1,000 times terawatt hour. And a terawatt hour, of course, is also a lot of energy. But be aware of that. That's a really big number. Okay, so now let's look into other types. Oil, similar, producing some other types of gas, but not so nice. You know the discussion about the diesel fuel in Germany, you might know. Natural gas is a little bit better, because natural gas, if you burn it, it is really clean. It is methane, and it produces only hydrogen and carbon. No, not too much of stuff that is unhealthy. By the way, biofuel, if you burn wood, you generate a lot of smoke, and I can tell you the story because I have a wood burner at home for my furnace to keep my house warm, and it's not really clean. That is definitely not the case. Solar at the rooftop. Why do we have people that die from that? Actually, if you put something on a rooftop and people work on top of that, they can slip away, and by chance they fall down from the roof, and that might be not the best thing for your health, and some people die. Actually, we have seen in Germany the cases that people have gone on the rooftop because there was snow on the PV and they wanted to have a little bit more energy. They tried to bring the snow away and slipping out because it's icy, and it's no, that's not a good idea. Really, don't go on your rooftop. That is dangerous. Wind power is a similar thing. Wind power towers are high, and during mounting them, there is a chance that you fall down. It's not often, but it happens sometimes. Someone forgets to use this security equipment and whatever. If things can go wrong, and that is really a thing, things go wrong. If they can, they go wrong. So hydro is really safe, but why do we have this number and that number? About 50 years ago, there was a very big disaster in China with a hydro dam, and it killed hundreds of thousands of people. And so if you include that in your calculation, and actually you should, because hydro dams usually don't go away, but if they do, they are really a deadly thing. So now look into nuclear power. Nuclear power has 90 on a global average. That is including the Chernobyl disaster and the Fukushima disaster. And so this number is lower than most of the other numbers. And if you have nuclear in a good territory like the United States or in Germany, you have no death toll death rate. What happens now in the world? Do we have a lot of nuclear power? Yes and no. So the first thing was, after this prediction from Eisenhower, people started to build nuclear power stations. And it was really growing more or less exponential until this big disaster in Chernobyl happened. Chernobyl was the real bad disaster. It was not a standard reactor as we use in the Western. It was a special reactor using graphite, and graphite can burn. And during this process that it ignited, all the radioactive containment, all this material in the reactor has split and gone into the air, and we had an emission all over Europe, and especially in the area around Chernobyl. So you see, new buildings, new constructions stopped more or less, and today there was another disaster, that was Fukushima. Fukushima was a disaster because 4 nuclear reactors had an uncontrolled situation, but on the other hand, it was not a Russian type reactor. It was a more or less a standard type reactor we also have here, and these reactors have a containment, and so most of the radioactive material was not going away. So after that, here was a big shutdown in Germany. You know, Germans stopped nuclear power. Others didn't care so much, and so the amount of nuclear power stations is not going up. It is slowly going down in the moment. So after this, the question is there a better way? And we have learned there's nuclear fusion. Nuclear fusion, if you use hydrogen, 2 types of hydrogen atoms, these are 2 special types. It's the H2, it's heavy water, and H3, it's tritium. Then you can smash them together and produce a new helium and a neutron. And they together spend you a lot of energy. That's the same, more or less the same process as in the sun. It's not exactly the same because the sun never burns H3 because that's not there. But the sun is, due to the fact that it's a really large star, it's a million times larger than the Earth. And so a fusion process is going on in the sun, but very slowly. It is, if you would be in the sun, if it's hot for us, if you have a liter of sun stuff in your hand, then this liter of sun stuff in the middle, it produces energy, but amazingly, this liter of sun stuff is not so much producing. It's 100 watt. That is 1 liter of sun stuff in the middle. So 100 watt isn't too bad. It's a little bit similar like your brain is producing also 100 watt if you see, I think now what I'm talking about. Now, good. So this is a way to produce energy. And if we look now how to do the details, and there is a saying, the devil is in the detail, and it's really true in this case. We were lucky because we had this first nuclear bomb, and it was incredibly easy to build a typical fission reactor. It was really done. The earliest thing was a fission reactor. But to build a fusion reactor, it is much harder. The problem is, to build a fusion reactor, you have to heat up to 100 million degrees Celsius. Now, 100 degrees Celsius is boiling water, and now try that 100, no, not 100 times, 1,000,000 times higher. That is incredibly hot. And if you look for some material that is able to sustain that, you won't find any. So you have to use very clever tricks. You have to use a torus-shaped thing. This is only a sketch out of a museum, and inside of this, not for people that are not here, is this hot material, and it does not touch the wall. The wall is not touched. No, don't do that. No, never touch that wall. But you can do that by magnets, and then you can produce the energy. So you need magnets to keep it in here. You heat this stuff inside. That is also tricky. Now, I should mention I worked 6 months in the Garching Research Center in nearby Munich, Max Planck Institute for Plasma Physics, to do that. As I was a student, and we actually built that stuff, and I was a little bit working with electricity connections and measuring the heat inside. That's quite not that easy as it looks, because you can't use a simple thermometer. So you have to heat that by microwave. That's one way. There are some others. Microwave is quite good because you don't touch it, never touch a thing like that hot. So, and then if it is really working and is really hot, you generate steam. Where do you generate the steam? Of course, not inside, outside here, somewhere here outside, you generate the steam. And then all is standard power station. Nothing really exciting. The exciting thing is what's going inside on. Now, this is a full picture of that. And now be aware what we just saw somewhere in here. What you're seeing here is big magnets and a lot of coils and a lot of additional equipment, incredible additional equipment, power lines for all these magnets, for the heating. Actually, I don't exactly see, but this lines may be part of the microwave. No, this seems to be the microwave connection here, and so on and so on. And what you have in reality is the following problems. Actually, that should be mentioned first. We are not ready. We have no nuclear fusion reactor. We may have one in 50 years or in 30 years, we don't know, but as long as the people talk about that, they always say in 30 years. And the worst thing is after 50 years, they now say 50 years. That's not good for a near-time problem solution. We have a low energy density inside here. Although it is really hot, you have to have a very huge system that you can burn a lot of energy. You need the tritium. Tritium is not nice because tritium is radioactive. And it's hard to produce, by the way. You have to produce it in conventional reactors or with some tricky equipment inside here. You need a very clean plasma. In the moment, it is in some way some iron or whatever is going into the plasma. It cools down immediately and the process stops. So that's very difficult. This first wall we have seen will degenerate over for years. Maybe after 5 years it's degenerated. But then you have a problem. You have to replace that. And look into this machine. Now a robot has to go in there, replace the inner part. It's not solved in the moment how to do this because it is radioactive inside. We have the neutrons. And in the moment, it seems that all this is very expensive. To give you an idea how expensive it is, you can see the site is a very big site here. That's the project, the ITER project in Europe. And in Europe, we tried to build a first reactor that is actually working a little bit in 2035. Now, let's watch out for the next 15 years. It should have a deuterium tritium operation. It is not designed to produce energy, not designed for producing, but it is a proof of concept. That means this machine will never produce energy. It will only show that it might be possible to produce it. And then after this year and after showing the concept, then we will start with the next, maybe another 20 years until you build all that, and then you have a working reactor, maybe. The price tag here in the moment is about 20 billion euro, but don't believe in first price tags of large sites. They always grow. So there is a very strange thing in the world. I want to have a short word about it because we still don't completely understand what happened in 1989. In 1989, the famous Fleischmann and Pons, two scientists and chemists, did an experiment because there were reports in the literature that platinum and palladium have not a defined amount of energy if you heat them or if you have electrolytic process in water. And so Fleischmann and Pons were really experts in measuring stuff like energy or heat in water. So that is a difficult thing. In the first moment, you think it's quite easy to understand that, but it is tricky. And they did the experiment. And the thing was, this was now heated days by days with more than 50 degrees. But usually, if you have water, you can try that at home and put it in a dewar. After 2 days, it's not anymore 50 degrees, and the heat is going away. So something strange happened inside here. We don't exactly know. Was it a fake? And they told us a fakey story, or is it really true? There is, some people think it was a source of nuclear fusion. I don't know. Now, I will give you now some new ideas. Nuclear power 2.0. By 2.0 now, yes, okay, that's a buzzword, and you can call it nuclear power 4.0, whatever you like. But I want to give you an idea why we should think again about nuclear power and some special issues here. So I go back to the things I already told you. Now we look a little bit different. To get an idea, this is a power station in Germany. It was Philipsburg, and it produced since 98 5 170,000 gigawatt hours. That is an extremely awful lot of energy. Compare that with the German wind power. So German wind power, and 2018 was a good year, and we have many wind power stations, and it produced only 110 gigawatt hours. No, there should be some more zeros here, but 110,000 gigawatt hours. Sorry for that. So 7 to 24 with long availability. We have no chemicals. We have high energy density. I already talked about that. And now we talk a little bit about the problems of conventional nuclear. There are 4 problems. The first one is the super-GAU, that you have a more or less uncontrolled reactor. A problem is proliferation. That means you can not always be sure that maybe some people build a nuclear bomb out of that. You have the disposal problem, what to do on the long run and how to construct that. So let's look into the detail. First of all, oh dear, what happened here? It looks very bad. A lot of animals are dying. 100,000 animals died. What was that? This was Seveso. This was a chemical disaster. Here again, a chemical site in Bhopal in India, and this chemical site did not run the right way and left 15,000 people dead. That is this number, by the way, if you go in literature, it's quite difficult. I took the number from Encyclopedia Britannica. There are some higher and a few lower numbers there, but we don't want to know that in detail. We know that this simple chemical reactor was able to kill thousands of people. So if you have technical systems, you always have a chance that things go wrong. Now, if you have technical systems and they are running well, they still may produce death by air pollution. In Europe, since 2012, we have 500,000 people dying from air pollution. This is not a number from some Green Party, it is from the European Union data. This picture, by the way, is not Germany, that is China. I took that picture as I was in Peking. That is a city with a real bad air pollution, at some days at least. And you saw the next buildings here, but the skyline of Peking wasn't visible at all. So bad was the air pollution. This is now nuclear disasters. So the first big nuclear disaster was 1979 in Harrisburg. There was no significant environmental impact. It was a type of warning that things can go wrong. Then in 1986, the Chernobyl disaster. As I was a student, it just happened and nobody knew exactly what was going on. So it was very difficult to understand and everyone was in danger. Now, today we have a very different problem. We have a coronavirus here and we don't know what's really going on. So it scares people. But finally, the people that died have people who really had to work in that area. That have been 31 direct deaths. But due to this cloud of pollution that has settled all around, there have been proposals of 4,000 cancer victims. That is, we don't know it exactly, but it may happen in that size. Fukushima, not so long ago, no, 9 years, there have been no direct fatalities and There might be a small number of cancer victims, but not comparable to the Chernobyl disaster, because the amount of radioactive material that was going off here is not comparable. That was a real worst case situation. So again, you can paint that. I did that already in the other slide. We have very low death rates in nuclear power, if we include the cancer cases. Now, how dangerous is nuclear radioactivity? That is a very difficult question, because we don't like to do experiments with people and radioactivity. So the first thing, we have seen 2 nuclear explosions in our globe on civilized areas in the city of Hiroshima and Nagasaki during wartime. There has been this explosion, and this explosion itself killed most of the people, the explosion. Second thing was the heat, that because there is a lot of heat that starts burning, and if you are nearby, you might burn your face and your skin, and that is deadly, and even your clothing will catch fire. So, and there is a nuclear fallout from this cloud that also is dangerous. So today we are quite sure that 90% of the death is really happening during the explosion due to forces and heat. Some are by radioactivity. Now, how dangerous is radioactivity? And there is one interesting story. In the 20s, long before these nuclear bombs were used, the people had the clocks, and the clocks had glowing numbers, and to make the clocks with glowing numbers, you can use radium. And this radium had to be painted on this clock, and during that painting, the girls usually tried to keep the brush stiff, and they used the tongue for that. And doing this is not so good, because you will incorporate radium. And there have been hundreds and thousands of girls doing this. They all are in a good age, and they didn't know that it is dangerous. But after the people detected that it is dangerous to work here, they did very precise studies what happened to them. And so we have results, scientific results about this event. And now I want to look into that. The first thing is radiation to counter radiation is not quite simple. You have special units called sieverts, and if you have 5 sieverts, that's an awful lot of radioactivity. You get radioactive sickness, and your lethality rate is 50%. 50% of the people will die if they have such a high radioactivity. That happens in a situation of a nuclear bomb, and so you can look into the numbers, and you can count the people that had a special amount of energy, and so you see the risk of dying. Now, the other thing is, if you don't have a nuclear bomb, but you incorporate a radioactive material, and so as the exposed workers, you can look if they have cancer. And usually you get bone cancer because the radium is going into your bones, and you look into that and you see if the dose is not very high, then you don't see any effect. But if you reach some level, somewhere in this range, then it gets dangerous. So if you have 1,000 times more than typically unexposed workers, you start poisoning your body and you will have cancer. So you don't have to be scared about very low radioactive situations. Why that? No, actually you are living here in the Black Forest. The Black Forest is radioactive. I did a measurement in my cellar, and the interesting thing is 1 meter, 1 cubic meter has 100 radioactive decays. Yes, not in a day, every second. Every second. Your cubic meter here is at 100 decays. Now you think that is dangerous to stay here, but be aware, your body contains Calcium-40. Your body has Calcium-40, and where is it? It is in your bones, and you have a similar activity of another 100 decays per second. How do you get to this Calcium? How does this enter your body? Usually by eating bananas. Bananas are radioactive, not strong radioactive, but all that is here in this range, and that is not dangerous. Only if you go beyond some limits, then it gets dangerous. Now, the next problem is nuclear proliferation. Nuclear proliferation means that states start to have nuclear bombs, and no one wants to see that. So if we look now on our globe, the green countries here in this land map have all nuclear power stations. And now guess who of them has nuclear bombs? Yeah, let's start the United States. Of course, we have nuclear bombs because they were the inventor of that. And some more countries, France, Great Britain, Russia, former United Soviet Union, and China. These 5 states are owning nuclear bombs, and there are the standard 5 nuclear powers on this globe. So during a long time, the country India and Pakistan started to have a nuclear bomb, and we now know North Korea has now a nuclear bomb. This very small place here. Have these countries also nuclear power station? North Korea doesn't have nuclear power at all. Some countries stopped having nuclear bombs after the destruction of Russia or the United States of Soviet Union, and they stopped having nuclear bombs. And South Africa had nuclear bombs. Now they don't have anymore. And the countries in South America, no, it's not the right tool here. The states of South America decided they don't want to have nuclear power. This small point, by the way, is a part of France, and so no, don't care about that. So nuclear power is here in many countries. Nuclear bombs have gone in some countries. A few of them have built them. And what's about this dark blue one, including Germany and Italy? They have nuclear bombs on their surface, but owned by others, by the United States. Yeah, that's a tricky situation. Actually, what we see is nuclear power stations and nuclear weapons are not directly connected. If you want to build one, you can do that without a power station. It might be even a cheaper way. And so we have never seen nuclear power station and a country with nuclear power that someone has stolen the stuff and produced a nuclear bomb. That did not happen, so luckily. Now the garbage. We have learned that there's a waste problem. Why is a waste problem? Because the radioactive stuff from our reactor is highly radioactive, because the uranium doesn't do always what it should do. It should do producing power and not producing radioactive plutonium, but it happens. Now, if you look into this place that is in Gorleben, you see all the nuclear waste of Germany. That's not a lot. That's a small amount. And actually, you can put the whole nuclear waste of this world, if you would really try that to have it very compact, you can put the nuclear stuff of the world into a cube with how many meters every year we produce? This is 8 meters, 8 meter sized cube. That is the world of waste in the nuclear age of 1 year. So yeah, you shouldn't put it so tight together. You should put it in good shaped barrels and keep it a little bit away that there's nothing going wrong. And then you wait and wait and wait until something happens. What can happen? Someone can ask, can I use that? And can I reuse that? That might be interesting. So we go into that. The repository question. Now, small execution. In the nuclear reactor, the fission products are produced, and all these fission products have a short half-life time, 30 years. So this 40 years is it's not really very short, but it is compared to other technical systems short. Especially if we compare that with dense uranium. And as already mentioned, in a reactor we produce so-called transuranium, that are elements that are have a higher number than uranium, and most famous is plutonium, and they have a half-life time of up to 10,000 years. And this is the core problem, this 10,000 years. So 30 years, 10,000, you see the real difference. So it should be mentioned that 99% of the original uranium at the uranium mine is not used at all, because it's uranium-238, and that is not usable in a conventional reactor. So now we can look into the question if there is any way to recycle that stuff, to reuse it. And now there is a chance, and I will look a little bit into this new ideas. Now, before that, another question about the economics of nuclear reactors. The price of nuclear reactors, and here it is the dollars in per kilowatt, and so it was set to 0 for the first non-demonstration reactor. So you know there is inflation and adjustment of different things, but somewhere we have to start. And so this is 1. The price of the first demonstration reactor was 1 per definition, somewhere happening here in 54. Now, after that, the different countries, we look here, United States, France, Canada, Germany, Japan, India, Korea, you see there is no Russia and no UdSSR because we have no real idea how expensive their system was. We look into these Western type countries. There's also no China in this list. There have been these demonstration reactors. They are usually expensive because you try new things. And then we start with the first real reactors in the Western world in the 60s. And then the price of the reactor first dropped. And then it has gone up. And especially, why did the price go up? Because the question for security was higher, and this is of course a reason to produce a better reactor, and the United States built very different types of reactor. The situation in France was not that bad. The price was growing, but not so steep. And what is with Germany? Germany, a little bit similar. What did France better? France has a standard type of reactor. And now other countries like Japan are quite good. The price is not going to explode. And there is one country where the price is going down. What's the reason? And here you see the first thing that you mention is they always build two reactors at one site. That really reduces a lot of questions because you have only one permit and all that stuff is reduced. The second thing is they have always the same type of reactor. They optimize them, and so they have some effect of serial production, and so they could reduce the price to the half of the beginning number we started here. That's quite interesting that the price depends very strongly on the way you do that and you build types of. So now we look to a very different thing. We look to so-called alternative reactors that are reactors built in a complete, or more or less complete different way. One idea is that you build a reactor in a way that it has no chance to have a runaway situation and to get destroyed by a thermal runaway. The second thing is that you try to use more sophisticated type of reactor core, and this is basically a so-called molten salt reactor. Molten salt reactors are not completely new. You have to know that in the 50s they already designed a molten salt reactor for an airplane, really for an airplane. Why for an airplane? At that time the situation was really strange. They had these nuclear bombs and they want to bring these nuclear bombs to Russia in the case of a nuclear war, and there have been no airplane that was able to do the full way. That means fly to Russia, drop the bomb and fly back. Because if you ask, oh, we have just dropped a bomb in your country, we want to land on your airport, that would be not a good idea. So we try to build an airplane that can fly to Russia and back without refueling. Actually, they built one of these reactors, but they stopped the program at the moment they had this rockets where you immediately can send nuclear bombs to the Russia territory. This is only for background. But now, if you use this molten salt, you have the molten salt inside of these pipes, and now if something goes wrong of this molten salt, then a so-called freeze plug will open. What is a freeze plug? This is a plug maybe from some metal like let's say zinc or so, or tin, with a low temperature freezing point or a low melting point. And you cool that. And if something goes wrong, if the cooling system goes wrong, or if the system in here gets overheated, this plug will open and all the radioactive material is dumped in so-called emergency dump tanks. There it is so split that no critical mass is here and it's easy to cool that. So now how does this machine work? Now let's start with the core. In here you have a very standard process. You have this uranium or thorium, by the way, that is another metal that is able to have this reaction. And now you try to you heat that surrounding, and this gets hot, and so hot liquid salt is going through that heat exchanger, and by a pump it's going again the way. So this is the primary cycle, and this heat exchanger is connected to a second cycle, and usually here you use water. And then you have a third cycle doing just the same as always, driving a turbine and some more turbines, and there's some details here, and coming back. So there are these exchange processes. You have a turbine, of course. At the final stage here, you have a generator, and the generator produces the electricity you are interested in. Now, there is, as always in life, something not so easy as it should be. And this is this small arrow here. What's going on here? There's a chemical processing plant. Why that? During the process of the reaction of the fission process, you have these new elements generated. And some of these elements will stop your nuclear process, and so you have catch these different elements, and this should be shown by this amount of numbers, so that you have a purified salt after that. The purification is necessary, and it is not so simple as it looks here, but it is possible. And finally, this reactor has always purified material in there. And the radioactive stuff that usually decays over 40 years is here catched. And most of it is really short-living, only a few days, but some of them up to 30 years, as we already learned. But the good thing is, due to the process, you don't generate the difficult elements like plutonium. So that has two advantages. You can't build plutonium bombs. You can't even build any bombs with this material because it is a completely different way you operate there. So we have no long way lasting waste, and the waste is immediately catch nearby the reactors for other reasons. Now, I don't know if this technology will come, but we have to look into, and we have to look into meaningful, useful energy sources. What are useful energy sources in our world? First of all, I think that we should use more solar energy in this world. Especially 80% of the world's population has enough sun every day to use photovoltaics and some storage, because you need storage overnight. You have no sun, and you can handle that with a power supply. The point is, there are some areas in the world, like Germany, where the sun is not available during winter time. There's only 4% of the sun as in summertime, and so we have to look for that something. We can store energy from the summer to the winter, but this is extraordinarily expensive. So we look for other sources. Germany has some wind, especially in the North Sea, and some other northern countries like Great Britain has a lot of wind, and Scotland produces today more wind energy than it actually can use in the North Sea that is really plentiful of wind. So because you need high-speed wind, if it is too slow for complex reason, we will go into that in the wind lecture, you can't produce it economically. Then during the times where you don't have stored energy, you don't have wind, you don't have sun, you can use natural gas to cover the gaps. If you do that, and we did simulations on that, there is only produced a few million tons of carbon. That is not critical for our global atmosphere and for the greenhouse. But be really careful, use only gas if there is no other way to produce energy in that moment. And their natural gas is not infinite, so we have from the beginning on to look for better ways. And one way is nuclear energy. And nuclear energy could substitute that in countries with little, where you have little sun and wind. And then, for example, look to Finland. This is a country that constructs just a new nuclear power station. So again, mixing the best sources might be the best way to solve the problem in the future for energy. So one word about science and some discussions you sometimes hear. There are people saying the global warming is not true. That is not science. That is meaning, because the physical laws behind the warming is so simple, and we go into that in another lecture. The point is the warming is true, and it is true because science can predict what's going on. It cannot exactly predict the temperature in 100 years at Furtwangen because many other things will interfere, but it can predict that it will go up 2, 3, or 4 degrees Celsius, and that will be on a global scale. There will be always points with a little bit different local climate, but it's dangerous to do things with a globe if you have only one. Another thing is air pollution. Science has found that air pollution is killing people. So be aware of this effect and use the scientific expertise to understand how many people die on air pollution. The same is true for radioactivity. There is scientific research, and there was a real big scientific research on the danger of radioactivity. And the numbers are low. There is a danger if you have a very high radioactive input, especially if you eat plutonium or so. That is definitely a deadly thing. But in the range that typically situations, even in a super-GAU, have, you can accept that it is not beyond the other problems. And that is always science to ask and to answer that question. So be aware of science. So if you want to have further information about this special question about nuclear power, I can give you some interesting places. There is a TEDx talk in Berlin. That's amazing. I'm not quite sure. I think it's in English, yes. And there is long but amazing, interesting talk from Kirk Sørensen. He is in this business since I think 20 years, and he knows everything, and he has a way to talk about the topic. I was really amazed. Listen to him.